Hello, this is Dr. Tom with a presentation on the Rankine cycle with regeneration as part of our review of thermodynamics. This material is in the reference handbook under thermodynamic cycle. So let's get started. Okay, regeneration is the process by which steam is drawn off from the turbine at various points and used to raise the temperature of the compressed water, which is called the feed water, entering the boiler. As a result, these regenerators are often called feed water heaters, or FWH for short. And there's two types, open and closed. Both can be used in the same system. However, the reference handbook only has at least a picture of an open feed water heater in its cycle. Open feed water heaters are really just mixing chambers where the water from the condenser is combined with the steam from the turbine, which is usually at high pressure, followed by a low pressure section. So in this case, you have just two fluids coming together and mixing and coming out as one. Closed feed water heaters, in contrast, are basically heat exchangers, parallel, cross flow, counterflow, etc., where you really have two separate streams and they are usually at two different pressures. And at least minimum, there's at least two pumps, one a condensate pump and a feed pump, the feed being sort of the main pump that we have already been looking at with just the basic ideal Rankine cycle. Okay, so add a lot of things here to get this open feed water heater added. This is basically the same diagram that is in the reference handbook. The pump number 2 is the one that we have really been talking about being our feed. Where you notice the difference here is over on the turbine. We have a high pressure turbine and a low pressure turbine instead of just a single turbine. We're drawing off steam at point 2, a value y, which represents how much of a mass flow rate is coming this way. Therefore, 1 minus y is going the other way, which you can see there just below 4, coming out of the low pressure turbine going into the condenser. So we have steam at 2 going into the open feed water heater. Then we have fluid. The steam comes out of the low pressure. It's probably high quality, goes into the condenser, condenses down to a liquid there at 5, goes into the, in a way, the condensate. That's the pump 1 is really the condensate pump, work going into that, and that is pumped into the open feed water heater. So what you really have is really basically two steams, but in that it mixes until it comes down to, by the time it gets out of the feed water heater, it is back to a liquid, saturated liquid, so that it can go into pump number 2 and follow along the cycle here. The Y again is called the bleed fraction, and that is a term used in the reference handbook, but what it is not given, and so I'm going to have to kind of show you how to actually calculate it. It really represents the M2 dot coming out of the high pressure turbine divided by the mass flow rate of the system, and that mass flow rate appears at 7, 8, and 1. 2 and 3 add together to be the M system, and of course over there Y and 1 minus Y would add to 1 there as well. 5 is got a 1 minus Y times M system dot, and we'll see that in the equations. Okay, the Rankine cycle using an open feed water heater reduces the mass flow rate through the condenser, which increases the efficiency. There's less to condensate, and the increase in temperature of the water entering the boiler also increases the efficiency of the boiler. So it's of course it doesn't come at a zero expense, so there's some economics that has to go into this, but it has proven to be useful, very useful in fact. Okay, so looking at the thermal efficiency, the heat engine's equation that we've seen many times before, eta W over QH. Again, the W is actually W net. The H is from the high temperature reservoir. I kind of like to write that as N thermal, eta thermal, W net over Qn, and that in terms of per unit mass, that would be W net over little q, lowercase qn, and because it's a cycle, the change in internal energy is zero, so W net equals Q net, so Q net is Qn minus Q out, and what is in the reference handbook in that section, the Rankine cycle with regeneration, is the efficiency Q dot N minus Q dot out over Q dot N. So that again reinforces the various equations that we've had for thermal efficiency based on how you want the units. Okay, and then of course it can be expressed again in a per unit mass basis, and this is essentially the thermal efficiency, and all of those are lowercase WQs, and the W out is the turbines. There's here clearly two turbines, low and a high, and there's at least here two pumps, at least in this simple particular system that we have here, and the QN is really the Q of the boiler. Okay, and again that can be put in terms of the rate of doing work, W dot turbines minus W dot pumps over Q dot boiler. So again, various ways in which this can be expressed. Okay, the turbine and pump work for the cycle must be accounted to separate flow rates, and so what we have here is these in the box there are all the equations that are provided with the schematic for the Rankine cycle with regeneration. The top one is the first one is the per unit mass of the high pressure turbine, and it's in terms of the enthalpies, H1 minus H2, and then the 1 minus Y H2 minus H3 going into the other part. Okay, and then there is the expression for W dot high pressure turbine, which really is just M system times the appropriate M system is multiplied through. So we've got M dot system H1 minus H2, 1 minus Y, M dot system H2 minus H3. So that's really the difference between those. And then you have the work per unit mass of low pressure turbine, although that's labeled, there's some typos in the reference handbook, and I have fixed those here. If you have just enthalpies, then you have per unit mass. So this one should, WLP turbine is actually labeled W dot LP turbine, H3 minus H4, but that would need a mass flow rate in there. And they do give you the W dot. Again, you would just multiply through by M dot system. Again, the bleed fraction Y is M2 dot over the M dot of the system there. Now I've given you what is not in the reference handbook. What is the total work per unit mass of the pumps? Well, pump 1 sees 1 minus Y of the flow rate, and then 1 complete M system for pump number 2. It sees the entire flow rate. Then the work per unit, we've done these before, are just the specific volume times the difference in pressures. For the first one, 1 minus Y V5 times P6 minus P5. And of course, all of these, you need to have the figure in front of you so you can keep track here, plus the pump number 2, V7 P8 minus P7. So it's just the specific volume times the difference in pressure across the pump. Okay, well now if we apply the first law to the open feed water heater, what we have going in is Y times M system times H2 coming out of the high pressure turbine, and then 1 minus Y M system coming out of the condenser is going to be equal to the M dot of the system H7, which is going into the pump number 2, I think, with all that. Okay. So you're essentially just accounting for the energy. 2 in, 1 out. Okay, so we can divide through by the M system to get ourselves just the enthalpies in the y and 1 minus y. Now you can expand that. We're going to get an expression for the bleed fraction y for this leaving the high pressure turbine. If you take the second term there and you've got a 1 times H6 and a y times H6, so you've got a y that gives you a y times H2 the first terms, and H6 a minus y times H6 equals H7. So what you can do is collect the terms in y, so you'll have y times H2 minus H6. Take the H6 to the other side so that you've got H7 minus H6. Then divide through by H2 minus H6 to give us this expression here. This is not in the reference manual, but it is useful to be able to sort of get it, and instead of trying to, because there's no equation in the reference handbook for how do you calculate y. They'd have to give it to you, which is very possible, but if not, how are you going to calculate it? Well, we're going to show you how to do that in some examples and problems. Okay, our first example here is we got a steam power plant operating on the ideal Rankine cycle with one open feed water heater. And I realize a real system might have lots of feed water heaters, open, closed, economizers, reheaters, I mean, just on and on and on, a real system. So we are keeping this within bounds here, either the ideal that we had in the previous lesson 1, and now this one with just regeneration and with just one open feed water heater. Okay, so we got superheated steam enters the two-stage turbine, the high pressure turbine followed by low at 10 megapascals and 500 degrees C. We're going to draw off steam at 2 megapascals from the high pressure turbine and direct it to the open feed water heater. Condensate is going to leave the condenser as a saturated liquid as usual at 20 kPascals, and after passing through the condensate pump is directed into that open feed water heater. We're going to use the notation presented in this lesson, which was the equation we just went over to determine the bleed fraction of the steam extracted from the high pressure turbine, basically y. Okay, so that equation that it came from the first law, H7 minus H6 over H2 minus H6. So what I'm going to do is find 4 H's. So from the superheat tables, we can get H1, 10 and 500, and we have H1 and S1. We need it. Because for the ideal Rankine cycle, for both turbines, they both operate isentropically, S2 would equal S1. And so for 2 megapascals and the above entropy, the enthalpy leaving the high pressure turbine is found to be 2,928.5 kilojoules per kilogram. Okay, then for 20 kPascals, we can find H5 and V5. We'll need that for the pump. So we have H5 is saturated liquid, 251.4 kilojoules per kilogram. And so H6 is H5 plus the work of pump 1. And pump 1 can be found from this expression V5 times P6 minus P5, and that the V5 again is 0.001 cubic meters per kilogram, and the pressure difference is 2 megapascals minus 20, so the megapascals is 2,000 kilopascals. So we've got that number, 1980 kilonewton per meter squared, but what you'll end up with is a kilonewton meter. A newton meter is a joule, so you'll end up with about 2 kilojoules per kilogram. So if we add that to our H5, doesn't add a whole lot. We actually could have just said neglect the work of the pumps, but I wanted to kind of show you where they fit it in here. So we got 251.4 plus 2, basically. Kilojoules per kilogram, so that's 253.4 kilojoules per kilogram. Okay, so for the 2 megapascals, the enthalpy for the saturated liquid can be found, H7. And now finally we have all the values that we need. H6 of course appears twice, so we needed just additionally 7 and 2. We found those, and we put those numbers in, do the arithmetic. We get the bleed fraction Y. This is the part that comes off the high pressure turbine into the feed water heater is 0.245, almost 25%. Okay, example 2 for this steam power plant of example 1, let's determine the thermal efficiency of the cycle. Okay, well, we can go through our thermal efficiency equation here and transition from the general Qin minus Q out over Qin, which you're given. Well, the Q you can divide through by the M dots everywhere to get the heat transfer per unit mass, and the Qin is going to be the boiler, the Q out is going to be the condenser. Now the condenser is only going to see 1 minus Y. Of course, the total is going through the boiler. So if we do that, the boiler is H1 minus H7, 1 minus the 1 minus Y times the difference in enthalpies across the condenser divided by, again, the boiler, H1 minus H7. And what you do is do the algebra and just get a 1 minus Y over H4 minus H5 divided by H1 minus H7. Now, from example 1, we've already found a lot of that. We found H1 and S1, we found H7 and H5, and we also have Y, 0.245. So all we need is H4, okay? And from the isentropic expansion, S4 has got to equal S1. And for 20 kPascals, we can find the SF and SFG and the HF and HFG. So the S4 is SF plus X4 SFG. So here we can find the X4. So putting in the value for S1, 6.60, and the other values, we get a quality 0.815. And so then we can use that to find H4. Okay, so put in the numbers again, the HF and HFG that we have, and get 2,172.8 kilojoules per kilogram. Okay, well, we can substitute now all these values into our thermal efficiency equation, H4, 5, 1, and 7, and do the arithmetic and get about 41%. Okay, well, that concludes the presentation. As always, we appreciate you allowing us to help you prepare for this exam.